It's bimodal. I just add the "ol" at the end. But so this, when there are two humps, bimodal. Thumbs up, thumbs down, get the gist? So what is this one going to be? Modal, yes. What is a term for the same? It's just a prefix, just like bi. Mono is one.
That's a yes, but remember bicycle. So one would be a
Uni. So what is this going to be? Unimodal, right? Because there's one hump. Now I do want to point one thing out. If I cut both of these in half, would they look the same on both sides? No. If I fold these over each other, would they match?
Yeah.
This one and this one.
Oh, no.
I mean, they won't match each other, but this side matches this side matches this side. What's that called? When things look the same on both sides?
Symmetrical.
Symmetrical. So they are what? These two? Symmetric. So these are words in math language we use to describe distributions. This one, what are we thinking? Okay.
Sock go.
All right. So what is a term when everything looks the same? If you're looking at a group of students, they're all dressed the same, they all look the same, same haircut. What?
Uniform.
Uniform. Does this look the same? Does this stay the same all the way through?
Yeah.
So what kind of distribution are we looking at? Uniform. It's not unimodal because there are no humps. You have to make sure there's a hump to be unimodal. Okay? Uniform. Now, what is different about 4 and 2? The what?
You got a little tilt
It's got a little tilt, right? Which way does it tilt, right or left?
to the right.
Tilts to the right, right? So the hump is a little to the right, and you have this tail.
Yeah.
We talked a little bit about things being skewed. Do you guys know that term? We didn't define it, really. But, so, this is a skewed graph. Do you guys think it's skewed right or left?
Yeah.
Right? It would make sense that it was skewed right. Yep, it's skewed left. So, in graphs, skewedness is based on the tail, whichever side the tail is on. So, we're looking, say our mode, right? Where's our mode going to be? At the top, right? This hump right here, this is our mode. Now, the mean, we've talked a little bit about the mean, it's the average of all the numbers, right? So because of this tail, our mean is going to be more like right here. So it's skewing the data to the left. This tail is pulling it towards the tail. Does that make sense? All right, now using all these terms we talked about, how do we describe 5?
Skewed bimodal.
Skewed bimodal. It is bimodal because there are two humps. Which way is it skewed?
Right.
Skewed right. Because the tail is to the right. Make sense?
Yeah.
Yeah, okay. So now we're going to go get into the actual activity for today. We got to stay standing though, sorry guys. I'm going to walk you guys through what we're doing. Alright, so there are 3 stations. One of them is dice, one of them is throwing pennies, and the other is stopping a stopwatch close to 5 seconds. So everybody come over here just a little bit so you can see what's going on. Okay, so if you're going to be in your groups, your table groups, there is this penny throwing and then there's penny throwing over there. There's a little tiny blue line. You're going to stand on it, if you guys don't mind. You're going to take your penny, you're going to throw it and try to hit the blue line. Yep. And then someone else in your group, nope, leave the penny, if you don't mind, going to measure for me how far away I am. There's a measuring tape right there. Someone else in your group is gonna measure how far you threw it from the line. You're gonna use the green side of the tape. Does it make a little more sense? So I'm at 1.4, and you're gonna measure it from the middle, okay? Does that make sense? From the middle of the blue line to the middle of the penny. Yeah? Alright, so that's station one.
Really?
You guys have to.
I just want to point out,
Yeah.
that tape measure is different than what you're used to in the sense that it doesn't have 1 feet and then inches. What it has done is it has actually split, it's called an engineer scale, but it has split each foot up into tenths. So like when you see 0.1, that is 1.1 feet. When you see 0.2, that's 1.2 feet, and then there's 10 marks. Just, it's more similar to the scientific units, or SI units.
So don't try to just write down 1.1 or 1.2. Make sense?
Or you can even go to 1.23, just
Yeah.
count the number of ticks. If you need help, please let us know. But we're using that green because it's going to be easier later today. Okay?
Make sense? And if you're at the pennies, you really have to work as a group because it takes forever. If one person is throwing their pennies, walking over, measuring it, writing it down. So work with your people, somebody measure for you, somebody record for you while you're throwing, and you're going to do that 6 times each. Okay? Make sense? Alright, the second table, we'll come to the jacks, is rolling dice. So, you're going to, this is really difficult, guys. This is the hardest table you're going to be at. You're going to roll dice that landed on 2. Guess what you're going to write down? A 2. You're going to do that 6 times. And then, at the bottom of your paper, I'm going to have to pass those out.
I was like, you want to just show them real quick?
Yeah. So, this top one is where you're going to put the die roll. You just write 3 more on the side for each of them. They only have 3 slots. Just make more. At the very bottom here, just fill in. You're going to roll 2 dice, and you're going to write the sum. So I rolled a 5 and a 1, 6. I'm going to write 2 die rolls, 6. And do that 6 times. And then you're going to do 3. Roll it. 6, 8, 1, got 11. Write that down. Make sense? Because the die moves really quickly. And then your last station is going to be a stopwatch. You're going to run the stopwatch. I'll have my phone at the table that's doing the stopwatch.
Did you ask Miss Williams if she has a stopwatch?
No, I didn't.
I'll go ask her real quick.
You're going to take a stopwatch and you're going to try to stop it as close to 5 seconds as possible. Right? So yesterday somebody actually got 5 seconds. It was really fun. So go ahead and head back to your seats. I'll pass these out and then we can start. You guys are starting with the pennies. So this is your line. You throw from here to that line. And then that's your measuring. So if y'all want to go ahead and start going, you can. You guys are starting with a stopwatch. I'll figure out if these games stop. This is starting with the die. No, because it's not, it's just a timer. It's not a stopwatch. You guys are starting with the pennies, so if you guys want to go ahead and start. Throwing your pennies, we're trying to land on the line. And then you guys are starting with the die. I think there should be enough for everybody to have 3. If not, let me know. I can grab one.
Timer on your iPads. Ms. Williams, she doesn't have timers, but she said that you can use the iPad timer.
Okay.
So they should have at least a couple iPads per group.
The graph is going to look like, so I can't really predict anymore because our data is up. We can see what these graphs look like. So let's talk about the rolling die. If we go back to start of class, what were those terms we used to describe graphs? One of them started with an S, I think. Right? With symmetrical was a term. What else did we use? Uniform. What? Bimodal. What was the other one? Unimodal. Were there any other ones? Maybe another one started with an S? What was that term when the data was leaning one way? Skewed. Skewed. Good. All right. Skewed, unimodal, symmetrical. Okay, so looking at, we're going to start with die. How could we describe this? You think bimodal?
Try.
There aren't that many humps, right?
Well, there's
There's 1, 2, 3. All right, I can see where you're getting that from. So,
there's not just, I thought it was 2 hard.
what do you mean? Like 1. So it goes up and back down. Because how these dots are placed, you guys see like here they're a little more close together than they are here. You see that? So in reality, when we roll die, because of how random it is, right, you don't choose what number your die lands on. You do it over and over and over again. We're going to get how would we describe that? Uniform. Right, because you have the exact chance for each number on that die to roll it. You have the same chance to roll a 1 as you do a 6. Maybe sometimes you're feeling lucky and you get 6 every time. But in actual probability, you have the same exact chance to roll that, right? Does that kind of make sense? So, the actual histogram or graph, we're going to use graphs, is uniform, right? And even though this does dip down a little bit each time, it's not enough to when you would sketch this graph, you would go down and back up, right? It's like 2 or 3 data points, so it's pretty uniform all the way around. Does that make sense? Not stock market. Stock market rises and falls at a time. Alright, now we're that goes here. I put it in the wrong one. Now we're going to go to the penny one. What are we thinking here? I know it looks a little funky, but it's the way our data points. I'm going to try to map it. I think it's the way dots are on here.
I will say this, realistically, what we thought we would see is a skewed right distribution, is what we were thinking. I would just kind of follow it a little bit though. Let's see what it looks like. Just kind of go outside of it. How would you describe that? Skew left maybe, there might be something else we would call that.
Maybe if we shut Tyler Coughlin down the office for a moment.
He's on his way. Dang Tyler, what'd you do, bro? Are they trying to find your backpack?
I'll tell you later.
Okay.
Think about these terms. Huh? Bimodal, right? It's looking a little bimodal. Because we have a little hump here at 1 foot and a little hump here over at 5 foot, 6 foot range-ish. Now we were thinking in this activity, the key they give you is it'll probably be skewed right. Thinking more people would get closer to the line and less would.
I think we also ran into the issue that the wall was there, so maybe first in the future if we do this, we do it across the front.
Yeah, that would make more sense.
Yeah, maybe we should also let y'all have a few practice throws, cause
Practice runs?
I don't think y'all, some of us realize that like, if you want it to bounce to the line, it needs to hit where first?
Way in front of the line.
Way in front of the line, right? I saw some of y'all like trying to make the penny hit the line, and I'm like, you gotta like toss it like halfway to the line for it to get there, so. It's all good,
It's alright, guys.
data's messy.
Yeah, data is not always gonna look like how we think it is.
I was gonna say that earlier, I meant to mention it. Part of the reason that we're kind of thrown off with that rolling one die situation is, it's not ever gonna work perfectly, especially when we do a small sample set. But in the long run, what proportion of our dice should have rolled a one? What proportion of what fraction of our dice should have rolled a one? Okay, how many sides are there to a die? So it would be 1/6, right? What proportion should have rolled a two? Well, like what? Not
How
a,
many
not a
sides of the
two.
die have a 2 on it?
How many twos are there?
1, so
So what proportion should have been? 1/6. There's only 1 2, isn't there?
Oh, yeah,
What proportion should have been a 3? 1/6. How many should have been a 4? 5, 1/6, and a 6. See how that should be the same all the way across? But that only works in the long run, right? If you take more statistics classes in the future, you'll talk about long run probabilities and it'll make more sense there.
and we are gonna show that to you guys a little better later. So now we're gonna talk about the stopwatch. What does this look like? Unimodal, right? It has one hump. Anything else? Symmetrical, right? It looks pretty symmetrical. Like all of our data is kind of centered around 5. We have a few on the outside, but they're far enough both sides on the outside, right? Like we have one at 4.5 and we also have one near 5.5, right? Kind of evens itself out. So, and y'all can write down these, either these graphs or these descriptive words we're using, like, okay, let's do this. So this is unimodal and symmetric. This is bimodal. And we said it was skewed. Which way did we think it was skewed? It was skewed. I think it's skewed left. You can see that. Is it? Okay. And then top one, uniform. So I get this down just so you guys know what each of these look like. I'll leave that for a second. All right, now we're going to get into normal and not normal distributions. This will be another fun thing we do on our vertical surfaces. That one. Yeah, okay, so in just a minute, once everybody's done writing down, I'll erase this. We're going to go with our groups to our vertical surfaces again, same ones you went to with the opening activity, with the 5, whatever. And you guys, using these terms we talked about, like skewed, symmetrical, unimodal, bimodal, uniform, all these things, you're going to use those words to describe these normal distributions. This is what a normal distribution looks like. And then use them to describe these non-normal distributions and see if you can come up with a definition for each of them. Okay? I thought you were looking at me. Oh, okay. All right, y'all can go ahead to your vertical surfaces and start. Okay, real quick, one more time. You're going to use those words we talked about to describe these distributions and try to come up with a definition for normal and not normal. Cool? These are normal. These are not normal. Alright. Oh. Sorry. Can you just go back to where you were?
I see an answer. Oh, you're right. Why are these?
She can talk,
But like, you're not gonna understand what I'm writing.
then try to write a little bit neater.
Use your group, talk about it, those terms we've talked about. Symmetrical, skewed, bimodal, unimodal. Ready? You have to describe what makes something normal and what makes something not normal. Using those words.
I'm a little blind.
Do you want me to draw them for you? Okay. So normal.
The words that you like electrical. It's like the phone, the.
These aren't gonna be perfect, obviously. Because.
Are all.
Hey guys, so one thing to point out is it's normal versus not normal.
There you go.
So you're coming up with a definition of what makes all those on the left normal and why
Alright, guys.
those on the right are not.
What makes the left normal and the right not normal? Maybe we'll try to do something Spider-Man later, but for now. Okay. Makes it normal?
Well, those are.
Okay.
These are.
Let's talk about that with them. I got 4.99. Talk with your group about normal, not normal though, that's what we're focused on.
Normally in one graph is not two. How do you think?
Right there. Spell it right.
We're gonna talk about this one.
No, it's single camel and double camel. You got it. That's why I can make it.
It's modal.
I know.
No, this is two.
I said all eight. I said,
I knew that.
Ain't modal?
What? Modal, what comes before that though? What does that mean? Oh, that's, it doesn't have to have a dash.
No, no.
Oh, yeah, AL, yeah.
No, they can take out the guy and make it will become worse.
I said all eight.
No.
It's AL.
It's AL,
No, Mike.
AL, modal.
You do like more.
Oh, so we're not gonna describe each individual one. So these are just some examples of not normal, and these are some examples of normal. You're gonna try to come up with what makes a distribution normal versus not normal. What elements of these makes them not normal altogether? So if they have this, they can't be normal, sort of thing. And if they have this, they have to be normal, right? Okay. What?
Well, all the regular ones, yeah.
All
Uniform
the normal ones.
at the
Anything
end.
else that we can say?
But
No, my.
I know you kind of
Put uniform.
Yeah.
Alright guys, you have about 3 more minutes to come up with a definition.
So what does it mean? What has to be true?
Maybe uniform, they match. They not normal.
Ah, there we go.
That's what you don't.
Just put everything.
Oh, so I have a question.
Oh, you put both
Are these unimodal?
Yeah.
But is it normal?
Wait, what makes it not normal?
You tell me. What is different? What do these have to not look like this? And what does this have to have in order to be normal? What does every single one of these three have that these don't?
I don't know.
Huh? All right, guys, come ahead to the middle. Join me. Come on. Okay. All right, what did we come up with? Normal doesn't have any outliers. More contrary data. Skew left, skew right. All right, I really. Are you guys sitting up at Kings or Queens? Kings. You guys aren't queens, but you're running on Kings. Okay. So, where's my marker? Okay. Thank you. All right. So I really like what the Kings did. Symmetrical and unimodal. Okay. So all three of these together are symmetrical and unimodal, right? Yes, no, maybe so? Tell me, yes or no? Yeah, there's one hump, and if I flipped it over on each side, they match, right? Now, but is this one symmetrical? Yeah, the first one is symmetrical, right? But what's different about this that makes it not like these? It's bimodal, right? What about this one? This is unimodal. It has one hump, but it's skewed to the right. Skew right. And then what about the last one? Skew left. So using these things, for something to be normal, what two things does it have to have? Symmetrical, but this is symmetrical, but it's not normal. What else does it have to have? Unimodal. It has to be unimodal, and it has to be symmetrical. Because these are unimodal, but they're not normal because they're not symmetrical. They're skewed. And this is symmetrical, but it's not normal because, why is it not normal? Because it's bimodal. It has two humps. All right? Y'all should have Frere models that you can write this down in your notes in.
Yes, behind the can you predict the shape, the one I would use is this normal versus not normal. You got the rest of class, so about 5 minutes to get all the notes you need to. You can even start on the check your understanding questions there and get started with that. Did you talk about which of these distributions would be most normal then?
Oh, yeah. So looking at these distributions we made, which one do we think is going to be normal? Or the most normal? Looking at like stopwatch, rolling die, and pennies, which one's going to be normal? The stopwatch, why?
On the other side.
What key features does it have? Unimodal and symmetric, right? So this is more normal, and one way the way we described it without knowing it was normal was all of our data is centered at this 5-second mark, and yet it goes out both ways, but evenly, right? We have a 4.5 and we have a 5.5. There's no far outlier. It's symmetric and it's unimodal. So remember that when it comes to normal distributions, what do they have to have? What two features does a normal distribution have to have? Unimodal and symmetrical. Good job.
Please, quick note, just understand we are being very hard on this because tomorrow we're going to study why does it matter that data is approximately normal, because there's a whole lot of situations in the real world that when you understand normality, it's really, really powerful. And so we're going to study the empirical rule. Please do note, nothing in the real world is actually normal. It's always approximately normal. So none of this is like, oh, it's going to be perfectly normal. but approximate normality will still come into play.